everyone, welcome back to Brainy Lab, your go-to spot for science made simple. Today, we're diving into one of the most important skills in chemistry, balancing chemical equations. Whether you're a student or just curious, you're in the right place. We'll walk through 10 real examples step by step, starting easy and building up to a bit more of a challenge. So grab a notebook and let's get started. Example 1, the formation of water. This one's classic. Hydrogen plus oxygen gives water. But is it balanced? Let's count the atoms together. Remember, according to the law of conservation of mass, in a chemical reaction, atoms are neither created or destroyed, but are just rearranged, meaning that there should be the same number of each individual atom on both the reactants and product side of the chemical equation. The reactants are on the left side of the equation, and the products are on the right. In this case, we have 2 oxygen atoms and 2 hydrogen atoms on the reactant side, left-hand side of the equation. On the right side of the equation, the product side, we have 2 hydrogen atoms as well, but only have 1 oxygen atom. This makes the equation unbalanced. To balance equations, we have to use the trial and error method. The more you practice balancing chemical equations, the easier it becomes. In this case, we have to add a coefficient of 2 on the H2O molecule on the product side, right-hand side of the equation. This leaves us with now 4 hydrogen atoms and 2 oxygen atoms on the right-hand side of the equation. You might be asking how we ended up with these new totals. Well, allow me to explain. Whenever there is an atom with both coefficient and a subscript number, we have to multiply the 2 to get the total number of atoms of that specific atom. In this case, we have a coefficient of 2 next to the H2O molecule, but the hydrogen atom has a subscript of 2. Therefore, we end up with 4 hydrogen atoms from multiplying the coefficient 2 and the subscript. 2 on the other hand, there is no subscript on the oxygen. There is no subscript number, meaning there is an invisible one. If we multiply the coefficient 2 and 1, we end up with 2 oxygen atoms. We are not out of the woods yet, because now only the oxygen is balanced on both sides. Having 2 atoms each on the other hand, the hydrogen is still unbalanced, having 4 atoms on the right-hand side of the equation and then 2 on the left-hand side. To balance this, we put the coefficient 2 on the hydrogen molecule, H2. This gives us 4 hydrogen atoms on the left-hand side as well, making the equation balance. You might be asking yourself, what a coefficient and what is a subscript? Coefficient in terms of chemical equations is whole number multiplier placed in front of a chemical formula to indicate the relative number of molecules of that substance involved in the reaction, whereas subscript in terms of chemical equations is a number written below and to the right of an element symbol to indicate the number of atoms of that element within a molecule. Example 2. For the second equation, we will balance the equation for the Haber process. The Haber process is an industrial method for synthesizing ammonia from atmospheric nitrogen and hydrogen gas, a crucial step in producing fertilizers that support global food production. Let's balance the equation together. First, we tabulate and compare the number of each atom on both the reactant and product sides of the equation. As you can see on the table, both nitrogen and hydrogen are imbalanced. On the reactant side, we have 2 nitrogen atoms and 2 hydrogen atoms. On the right-hand side, 1 nitrogen atom and 3 hydrogen atoms. Let's now balance the equation step by step. Step 1, we put a coefficient of 2 on the NH3 on the right side of the equation. This step leaves us with 2 nitrogen atoms on both sides of the equation, leaving only the hydrogen atoms unbalanced, 2 on the reactant side and 6 on the product side. To balance the hydrogen, we put a coefficient of 3 next to the diatomic hydrogen atoms. Now our equation is balanced. We have 2 nitrogen atoms on each side and 6 hydrogen atoms on each side. Now let's move on to the following equation. Example 3, combustion of methane. Combustion of hydrocarbons is an exothermic reaction that releases significant heat and light. These reactions always produce carbon dioxide and water. First, we tabulate and compare the number of each atom on both the reactant and product sides of the equation. As you can see in the table, carbon is balanced on both sides of the equation, with one atom on each side. However, the oxygen is unbalanced, with 2 and 3 atoms on the reactants and product sides of the equation, respectively. The hydrogen is also unbalanced, with 4 and 2 atoms on the reactant and product sides of the equation, respectively. Let's now balance the equation step by step. Step 1, we put a coefficient of 2 on the H2O molecule on the right-hand side of the equation. This step leaves us with the carbon and hydrogen atoms balanced, with 1 and 4 atoms on each side of the equation, respectively. Only oxygen remains unbalanced, with 2 and 4 atoms on the reactants and product side of the equation, respectively. To mitigate this, we put a coefficient of 2 in front of the diatomic oxygen atoms on the left side of the equation, leaving us with 4 oxygen atoms on the reactant side, matching the product side. Now our equation is balanced. Now for our fourth equation, we are going to balance the equation for the classic reaction between sodium and chlorine to form sodium chloride. Sodium chloride is our regular table salt. This reaction is a simple combination of a metal and a halogen to form ionic salts. As shown in the table, the sodium atom is balanced on both sides of the equation. The chlorine atom is unbalanced in the equation, with 2 atoms on the left and 1 on the right. In this case, using the trial and error method, we set the coefficient of the sodium chloride ionic salt on the right-hand side of the equation to 2. This step leaves us with 2 chlorine atoms on both sides of the equation. However, the sodium remains unbalanced with 1 and 2 atoms on the left and right side of the equation, respectively. We then add a coefficient of 2 next to the sodium on the left-hand side of the equation, and just like that, the equation is balanced. Now we are moving on to more complex chemical equations. For our fifth equation, we will balance the equation for the reaction between calcium and water. Metals react with water to form metal hydroxides and hydrogen gas. If you could let me digress a little, did you know that a lit splint is used to detect hydrogen gas in chemical reactions? In the presence of hydrogen, a lit splint ignites and burns quickly, making a popping sound. Now let's go back to our equation. As you can see in the table, only calcium is balanced, with 1 atom on each side of the equation. Just to let you know, in this equation, on the right side, we have 2 atoms, namely hydrogen and oxygen, enclosed in a bracket, and outside the bracket is a subscript of 2. Now what does this mean? It means that the subscript 2 applies to all the atoms inside the bracket. This means that, in this case, we have 4 hydrogen atoms and 2 oxygen atoms on the right side of the equation, which does not balance with the 2 and 1 atoms of hydrogen and oxygen, respectively. To balance this equation, we put a coefficient of 2 on the H2O molecule on the left-hand side of the equation. This increases the hydrogen and oxygen on the left-hand side of the equation to 4 and 2 atoms, respectively, which in turn balance with the atoms on the right-hand side of the equation. Now our equation is balanced. For our sixth equation, we will balance a chemical equation of the reaction between aluminium and oxygen to form aluminium oxide. This equation is classified as a redox reaction because it involves electron transfer. As we can see in the table, neither aluminium nor oxygen atoms are balanced on both sides of the equation. Aluminium has 1 atom on the left side of the equation and 2 on the right. At the same time, oxygen has 2 atoms on the left side of the equation and 3 on the right-hand side. The first step in balancing this equation is to assign a coefficient of 2 to the aluminium oxide on the right-hand side. This step results in the aluminium and oxygen on the right-hand side of the equation increasing to 4 and 6 atoms, respectively. However, our equation is still unbalanced. To mitigate this, using the trial and error method, we assign a coefficient of 4 to the aluminium atom on the left-hand side of the equation. This leaves us with aluminium balanced on both sides of the equation. To balance the oxygen, we assign a coefficient of 3 to the oxygen atoms, which in turn balances the oxygen on both sides of the equation. And just like that, our equation is balanced. Our seventh equation is the reaction between iron and oxygen. This equation is very similar to the previous one, so I will leave you to balance this one. Pause the video and then try to balance it yourself. After trying, you could resume the video to see if you nailed it step by step. For our eighth equation, we will balance the combustion of propane. As seen in the table, we have 3 carbon atoms on the reactant side and only 1 on the product side. At the same time, we have 8 hydrogen atoms on the reactant side and only 2 on the product side. This does not follow the law of conservation of mass. Let's rectify this together. As we can see, the shortage in the total atom count is mainly on the product side, so we will start there using the trial and error method. First, we assign a coefficient of 4 to the H2O molecule on the product side. This increases the counts of hydrogen and oxygen atoms to 8 and 6 respectively, which in turn balances the hydrogen atoms on the reactant and product side. Next, we assign a coefficient of 3 to the CO2 molecule. This step increases the number of carbon and oxygen atoms to 3 and 10, respectively, thereby balancing the carbon atoms on both sides of the equation. Now only the oxygen atoms remain unbalanced. To mitigate this, we assign a coefficient of 5 to the diatomic oxygen on the reactant side. Now our equation is balanced. This one was a bit complex, but it all becomes second nature with practice. Our following equation is the classic decomposition reaction. This one is used in labs to generate oxygen. In this reaction, potassium iodate decomposes to form potassium chloride and oxygen. Let's balance the equation step by step. First, we tabulate the atomic totals on each side of the equation. We can see in the table that both potassium and chlorine atoms are balanced on both sides of the equation, with 1 atom of each on each side. Only the oxygen is unbalanced, with 3 and 2 atoms on the left and right side of the equation, respectively. First, we assign a coefficient of 2 to the KClO3 compound. This increases the total number of potassium, chlorine, and oxygen atoms on the reactant side to 2, 2, and 6, respectively. This leaves the atoms on the product side short. To mitigate this, we assign a coefficient of 2 to the KCl compound on the product side, which in turn balances the potassium and chlorine on both sides of the equation. To balance the oxygen, we assign a coefficient of 3 to the diatomic oxygen on the product side. This balances our equation. For our final equation, we will balance an acid-base reaction, also known as a neutralization reaction, between nitric acid and calcium hydroxide. Acid-base reactions always produce a salt and water. Let's get into it right away. First, we tabulate and review the atom totals on both sides of the equation. I will leave this one again for you to practice. You can pause the video and attempt to balance the equation. The answers will be in the following slides, step by step. I hope you found this lesson helpful. Here are more equations for you to attempt on your own time. The answers will be in the comments. Let's summarize what we have learned today. 1. We explored 10 types of reactions. 2. Practiced systematic balancing. 3. Applied stoichiometric principles. Please like, subscribe, and comment with any questions.